Hi everyone. This is a quick recap of chapter 2 about the vectors of the book Coding the Matrix, and this is accompanied by the Jupyter notebooks that I'll also be sharing. So let's get started. So initially, chapter begins with a description of what is a vector. So a vector is defined over a field like R or GF2 or complex numbers or any other field, and it goes from so here this is a 4 vector. So four vector means 4 elements of the field R. So that is called a 4 vector. So just and the parentheses is the commonly used notation for a vector. And so also the set of all vectors, which all vectors with 4 elements that have real numbers, can be represented by this notation R4. And this might also remind you of this notation RD, which is the set of all functions from D to R, but there are slight differences. So vectors can also be interpreted as functions itself. So in here, the 4 vector from R4 can be also represented as a function where the domain is 0, 1, 2, 3, and it goes to the real domain, and the mapping is defined as 0 to pi and 1 to e and 2 to -1 and 3 to 2. So also that if you remember, this is again fd is the notation for functions from 0, 1 to up to d-1 to f, and this can also be represented as a vector from d to the field f. So for example here, g2 to the power 5 is a 5-element bit sequence. And also you can in document retrieval you can also have a vector from words to R. So each word has a score, for example, and then you are doing just so if here it will be R to R exponent words. That notation will mean all functions from words to R, and that could also represent a vector. Well, a vector of yeah, we'll go to the sparsity thing later, but you could also have, like, for example, each word is an index, and whether it's present or not is the vector. So that's the vector here. And d vector over f is a function from d to f. I think we went through this. Okay. Our next slide is representation of vectors using Python dictionaries. So here the book goes through and tries to represent a vector using a Python dictionary. And what it does is the good thing it does is it makes it independent of the domain. So generally a vector, if you represent a vector as a function, you'll represent it like this. So the first 0th index is this, the first index is this, the second index is this, and the third index is this. But this won't allow word vectors over R. So what they do is, so here, if you see the rain in Spain falls mainly on the plain would be represented by this dictionary. But this dictionary cannot be represented in this form. So what they do is, so we can just remove the elements that have value 0. So for example, here USA has value of 0, so it's not even used here. So that idea can be used in the Python implementation of vectors. So sparsity is like a vector, most of whose values are 0 is called a sparse vector. So if you are using a vector from words to R to depict a document, then it will most likely be a sparse vector, because most of the words will not be there. So also, let's go to the main slide. And also, if a vector is sparse, so most of the values are 0, then a vector is called k-sparse if there is a guarantee that that no more than k of any of the entries will be non-zero. So that will make it k-sparse. So, for example, it gives an example that most signals acquired by physical sensors, images, sound, are not sparse because each of them has value. Each channel has a value. But it also goes through goes through techniques like PCA, which makes which actually shrinks the channels and makes it reduces the number of components. So what can be represented with a vector? So what all things can be represented with a vector? A document can be represented by a vector using the bag of words model, or a binary string could be represented by a vector, and the algebra could be defined over GF2 field, and then a collection of attributes, for example, can be a vector. So, for example, your Senate voting record of all senators could be vectors. For example, one is a yes, 0 is a abstain, and -1 is a no. And then you can define a vector on top of, if you define a algebra on top of that, then you can define a voting record vector on top of that. And then there is demographic record of a consumer. So consumer's age, race, everything, that whole thing can be considered a vector. Characteristics of cancer cells, the ACTG sequences can be a vector. State of a system can be a vector. So population of different countries can be represented as a vector. Number of and then state of a pseudorandom generator at various times after each output can be a vector. And there is a game outlined where Lights Out in the book, where you have you have kind of a touchpad with multiple buttons, and you can and every time you press a button, the button lights up, or it lights up or gets switched off depending on what the previous state was. But the same thing happens to all the other cells directly adjacent to where you are pressing. So in this case, this problem can be modeled by a vector addition, and then you can there could be a problem of whether this keypad can be switched off from this state totally. Could be like whether a vector addition would yield a 0 at some point. So also probability distributions can be vectors. So for example, probability of 1 is 1 by 6. This is a uniform probability of a dice that is represented as a vector. Also, an image can be a vector. So the way that is like 0, 0, 1, 0. This is the domain of the vector. These are the pixel values of the of each pixel. So that way, an image becomes a vector. Then can interpret the what can be points. Can interpret 2 vector xy as a point in the plane. 3 vectors as points in the space. So same idea as images. You can have a set of points as a vector. So or in 2 dimensions or 3 dimensions. So if you have 3 points, if you have a point, then in 2D, then it will have 2 values. In 3D, it will have 3 values. Now, vector addition. So vector addition, translation, it's also can be interpreted as translation. So you take a number z, and you add, like in complex numbers, you add the 1 plus 2i. In vectors, you will add each component to its corresponding component, and that way this is also called translation. So similar to complex translation, and also translation with and vector addition. So this so this is still translation, and suppose we represent n vectors by n element lists. Okay, write a procedure to compute the sum of two vectors to so represented. So this will be very similar to this add method, but this is also in the notebook. Also, these can be found in the notebook. Zero vector. So zero vector, a D vector, all its entries are zero, is a zero vector. A zero vector has every element is the identity element of the algebra. Also associativity, because the field that is used and the algebra that is used is associative. That's why you could also show that vector addition is associative. Similarly, by the same logic, you could show that vector addition is commutative. And one thing I forgot to mention is that vectors, by vectors, we also mean that the domain of the vector, if vector is associated with a function, the domain of the vector has to be finite. It cannot be like real numbers. It has to be like numbers from 0, 1, 2, 3, 4, 5. So so vectors, the size of the vector is finite. In other words, vectors has arrows. So vectors have arrows. So here you could see that a two vector, same as complex numbers, 3, 1.5 can be represented as this vector as well as this vector, depending on where you choose the origin to be. And vectors has arrows, like complex number, addition of vectors over R using arrows. Tail of U to V. Okay, so addition of vectors can also be interpreted something like this. So U plus V is, it can be geometrically interpreted as completing the hypotenuse on this triangle, not hypotenuse, but the third side of the angle, which can be proved. Also, scalar vector multiplication. So when you scale a vector with a scalar, then all that happens is, let's go to the last slide. All that happens is you go from alpha v1 v2 vn to alpha v1 alpha v2 alpha v, which can be geometrically shown to be, this will be on the slides, but this can be geometrically shown to be just the size of the arrow just increases by twice. So that's the only thing, and you can place it on any origin. So that's the scalar vector multiplication. And let me see if there is anything I missed. Okay, scalar vector scaling arrow. So it can also be proved that the scalar vector multiplication is associative. So alpha beta v is alpha beta v. This follows from the same commutative associativity of multiplication of the elements of the vector which are drawn from a field. Also, the book goes through. So for example, if you take a vector 3, 2, and you plot you multiply it with all scalars from 0 to 1 spaced by 0.1, then you will get something like this. And then if you, so this is 0.9 V, this is 0.8 V, this is 0.7 V, this is 0.6 V, 0.5v, 0.4v, 0.3v, 0.2v. So similarly, so this idea can be used to construct a full line segment. So for example, if you let alpha to be anything from 0 to 1, and you choose origin to be 0, then this will compose of all points from 0 to 3.232 in a straight line. So that's what so this is the formal definition of it. So if you let alpha between 0 and 1 and real numbers, then if you choose v, then it will be alpha v will represent all points on the line segment between origin and v. So that's and also lines through the if you multiply by anything greater than 1, then the point that will be covered is will be the vector that will represent will be bigger than the original vectors. Negative scalars will just point in the opposite direction. When you multiply a vector with a negative scalar, the vector will point in the opposite direction. Also, what if we let alpha range over all real numbers? If we let it range over all real numbers, then it will span the whole line, not the line segment, but line in the direction of the vector. So that's and lines through the origin. So if for example you are concerned with alpha v, then it will pass through origin, because when you put alpha as 0, then this will definitely have the 0 point of your algebra. So this will represent a line through origin. But if you combine vector addition and scalar multiplication, then you can get all lines, all possible lines, even those who do not pass through origin. So for example, let's go here. So this will represent a line going from 0.51 in the direction of the vector 3, 2. So 0.51 in the direction of the vector 3, 2. So that's the vector addition and scalar multiplication. Combining vector addition and scalar multiplication, you can also so that's about it for scalar multiplication. There is also this from the same scalar vector multiplication over. So it also follows the scalar multiplication also follows the distributive laws, just follows directly from the field laws, so from the real number laws. Vector addition and scalar multiplication. And so there's one more important result here, that if you, for example, want to figure out all the points between 0.51 to 3.53, then you can construct something like, at the end, what you will get is a construct like this: alpha multiplied by 3.53 and beta multiplied by 0.51, where alpha plus beta add up to 1. So this will constitute of all points, all vectors between 3.53 and 0.51 on the straight line between those 2 points. So that's the result. Okay, this is also called a convex combination. Okay, so the same. So this is a nice example where the same concept can be applied on pictures. So you can take, so for example, if you take 2 pictures and represent these 2 as vectors, and then you take half of this and half of this, then you get a picture like this. And all these points are, all these images are basically points on the straight line between the 2 images in that high dimensional space. So for example, if this was a 10 cross 10 image, then in a 100-dimensional plane, all these pictures are points that lie on a straight line. So so that's the result here. And okay. So also addition can be defined, like I was mentioning, also addition can be defined over other fields as well, like GF2. So here, but so here 1 1 goes to 0, 1 0 goes to 1, 1 1 goes to 0. So also, so then the book comes to perfect secrecy. So Alice and Bob agree on the following 10 vector. So let's suppose Alice and Bob decide on a key that they use one time, and then Alice wants to send a message to Bob. So she wants to send P to Bob. What she will do is she will just add K to P, and she'll send it to Bob. And Bob can decrypt using, again, a C plus K, because minus is equal to plus in GF2. So so from the ciphertext, the plain text just follows by adding the key again. And then okay, if the key is, then the theory behind perfect secrecy is that if someone looks at your ciphertext, the probability of it having come from any plain text is equal. So it's uniform distribution over any plain text. So depending on the key, if you don't know key, then depending on the key, it could have come from any plain text. So any plain text, when applied to a particular K, will yield that ciphertext. So any plain text is equally likely. So if you take, for example, plain text was 0 0 and your ciphertext was 0 1, then your key could be 0 1. If you're plain, so depending on the key, if you don't know key, then your plain text could have come from any plain text could be any value. So that gives you the guarantee of perfect secrecy. Okay, so it goes on to give another example. So if the author has a midterm exam in a binary file, what it does is it picks up a key, the same length as the binary file size, and then what he does is he let me go to that slide, the full slide, and then when he adds it to the original midterm, whatever he gets, he gives it to 2 TAs. So the key and key plus the original text. So none of them can together determine what their answer sheet is. But when they get together and add their values, they will get what the plain text is. So that's and both of them cannot figure out what it means without getting the key, and the key is with the other person. Okay, all or nothing secret sharing using GF2. Well, RSA just introduced the product something like this. So lights out, I was explaining, is a cool example. So in lights out, what happens is, okay, let me go. And so this is a touchpad where you have a number of keys. Some of them are on, some of them are off. Now, depending on where you press, so for example, this is a button press vector. So it gets pressed here, but it also affects all the directly neighboring cells, and all of them get a state change. So now this can be a vector, and this can also be a vector. And if you interpret it as a 2D vector in GF2, then it can also be, the state changes can also be interpreted as just additions. So for example, from this state, if you press at the top left corner, then this will be the resulting state. And this can also be a GF2 multiplications addition. So 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 0 is 0, and 1 plus 0 is 1. So this is just a vector addition. And similarly, the other one is also a vector addition. Then here as well, it's a vector addition. So you could see it as a computational problem to find the button vectors that take touchpad from one screen to some particular S, to some particular state. Okay, so all right, vectors over GF2, lights out. Find vectors whose sum equals S. Solve an instance of which set of button vectors sums to S. So you've given a certain state S. How would you get to that state? So all you have to do is find a subset of GF2 vectors whose sum equals S. So it can be modeled in a different way. So for example, in this case, you have to find some in a 2x2 grid. How would you get to this this state? So first you will press the bottom left, then you will press the bottom right, and then you will push the top right, and you'll get this state. Okay, so now let's get to dot product. So a dot product is defined as basically you go through each element in order, and you multiply them together, and you sum the results that come up. So it actually gives you a scalar in the end. Output is a scalar, not a vector. Dot product is also called scalar product. So something like this, 1, 1, 1, and this number, if you do a dot product, then 1, then it comes out to be minus 30, because 1, you could see 40 plus 20 plus 10, 70 minus 100 is minus 30. So this you will do in the notebook. Let's not go there. So dot product, so for example here, you could find the total cost of beer using the dot product of the cost vector and the quantity vector. So if you have cost is 2.5 per ounce for hops, and malt's price is 1.5, and similarly, then you multiply it with how much quantity there is for each of them. So the quantity used is this much. So 6 ounces of hops, 14 pounds of malt, 7 gallons of water, and 11 grams of yeast. And then you multiply them together. So you're basically taking a dot product, and it will give you a scalar value, which will be the price of the cost of making the beer. So here does it say how much it is? No, it doesn't, but 40.992 is how much it will take to make the beer. Similarly, so you could also represent linear equations with a dot product. So let's suppose you don't know. You're given. Let me come to the final slide and then. Dot product linear equation. Yeah. So here, if, for example, you're given okay, we'll go through this. So you could point it to something like this, where A is a vector, beta is a scalar, and X is a vector of variables. So this is just so A is a vector of, for example, real numbers, and X is what you have to find, variables, and beta is something you know is again a set of real numbers. So duration multiplied by rate is beta I. So can we find number of entries of rate? So can we find this X given A, X, and beta? Can we find this X? More general equations. So you could also have more generally, you could have m of these equations, and can you find a X that satisfies all of them? So this will come in future weeks as to how to handle these kind of problems, whether they have only one solution or multiple solutions or no solutions. So those things will come in later chapters. And so here, dot product can also be thought of as measuring similarity between vectors. So if a dot product is also considered to be the cosine of two vectors, the cosine of the angle of two vectors. So if you recollect, cosine is highest when the angle is 0. So if they have like the same direction, the cosine will be 1. But if they have like totally separate directions, then the cosine is going to be -1. So dot product can also be interpreted as a distance measure. So so that's why you have something like this. So and similar, so dot product can be used in multiple ways. If you have like a short clip and you need to figure out how similar it is to a long clip, to a portion of the long clip, what you can do is you can slide the short clip, which is basically a vector, throughout the longer vector and see what the dot products are, and take out the one that has the highest dot product, and that will be most similar. And also, same thing, you basically take this short one, slide it over the longer sequence, find the one that yields the highest dot product, and you have the most similar audio segment. Okay, you can use the fast Fourier transform to do all these dot products quickly, and consider the dot product of this. So dot product can also be defined on GF2. So for example, GF2, the algebra is basically modulo 2. So in here, if you do dot product of this vector with this vector, then you get like 5 products, 1, 0, 1, 0, 1. When you add them together, you get 1 and 1 cancel out, and modulo 2 addition, 1 is left. So the answer is 1. Similarly, the other one. Okay, so now the book goes through a simple authentication scheme, a challenge response system. So computer knows a password, a human knows the password, but the computer does not want to ask the password directly. So what it does is it actually gives you a challenge, and humans adds the key to it and sends it back to the computer. Computer, because it knows the key as well, adds the same key to the same value, and it can figure out if the human has the actual value or not. So it's potentially safe against an eavesdropper if they can only if they can only see the question once. But there is some problems with it. So, okay. How would you attack a simple authentication scheme? So one way to attack this would be that if you, for example, see all the values and all the answers, then you know that that if you get another value that is a sum of the questions. So if you, for example, get challenges as A1, A2, AM, and their responses were beta 1, beta 2 up to beta M, then if you, for example, the next challenge that comes is A1 plus A2 plus AM, then you can see that the response would also be beta 1 plus beta 2 plus beta M, because it follows from the same thing. So because this can also be interpreted as a dot product. So what can happen is A1 plus, if you just leave these dot dot dot, if you sum A1 A2 AM, then it will become A1 A2 AM multiplied by X is beta 1 beta 2 beta 1 plus beta 2 plus beta M, which is what the computer is looking for. So if I can figure out that your challenge is a sum of a subset of something I've previously seen, and I'll just sum the answers from the previous rounds, and the computer will accept it. So that's what is going on here. And also, so dictionary-based representation of vectors. So this, in this, so basically, the good thing about this representation is that it basically takes a domain and another function, and the way it handles is it has a domain which is a set of list of labels, but the actual values are basically just invocations of this function. So if you set a function, set an element, then it sets an element from the domain to the value. So if for example the domain is words and the values are real numbers, then you only get a set of functions, and you can set, for example, set San Francisco to 1. So then this vector will have a 1 for San Francisco and Chicago and Dallas, but for example, not for New York. So this way you can have a dictionary, you can have a domain independent representation of vectors. Otherwise, if you just have one line, then you can only have real number, like integers as the domain, integers starting from 0 to a finite number. But this representation allows you to have arbitrary domains as vectors. And so that's what they go through the implementation. You can see it in the Jupyter notebook. So setter and getter, they're actually defining all the different operations in this. So f is actually not a function but a dictionary, and then they are so that was my mistake. I thought it was a function, but f is a dictionary, and then using d and f, they are defining all these functions: get item, set item, and all the other. And there is a notebook about it, so you can do it for yourself. Okay. Is there anything else? So list to vec, you can have a function list to vec such that you can compute the domain, and then you can have a vector representing the list. So also there is this. The book mentions a triangular system of equations. So so by triangular system of equations, what means is, if you see, only the upper triangle of this matrix or set of vectors has a real value. All the lower portions. So this is a 4 cross 4 vector, and all the lower ones have values of 0. In this case, solving this equation becomes pretty easy. So it can also be represented as something like this. And to solve this, what you can solve is you can trivially solve for x4, then you plug that x4 value into this one, then you solve for x3, then you plug x3 and x4 here, then you solve for x2, then you ultimately solve for x1. Now what you can do is, so this is the, okay, now they're getting at like Python implementation, which is also there in the notebooks. So let's get that. Now, this technique is also called the backward substitution technique. And so there's also something in the book that when does it not have a solution? So if any of the, in a upper triangular system, if a upper triangular set of equations, in this one, for example, this was 0, then this would not have a solution, because 2x3 is equal to 3. The only way it can have a solution is if these two are just the same. So if this was 5x3 and this was 15 and this was 0, then these two will mean the same thing. So any x3 will satisfy that. So you will basically have infinite number of solutions here. Otherwise, it will have 0 number of equations. So that's what happens. That's what will happen in case one of these diagonal entries are 0. So that will not be a good. Okay. So that's pretty much the gist of this chapter. And if you follow with the notebooks, it will give you a better idea. Thank you.